So welcome everybody to the Flow seminar series. Today's talk is by none other than Eduard Gorbunov from FISTEC, Yandex, and Sirius. So Eduard is a PhD student at MIPT in Moscow, and he was a member of my group when I was a visiting professor at MIPT. He was working for a couple of years in that team and has done some really wonderful work. So it's really great pleasure that I can introduce him today. And he also is a serial intern in my team, in my lab at KAUST. So thanks a lot for all that you've done so far, and also for agreeing to give a talk, which is joint with the All Russian Seminar on Optimization. Eduard will talk about a recent paper that he co-authored on linear converging error-compensated SGD. I think this is all I'm going to say. Maybe I have just one or two sentences. That Flow is a one world seminar series in federated learning. We aim to cover all aspects of federated learning. Of course, we cannot do that right from the start, but this is our goal. We're here for the long run. We'll keep doing this, and aspects such as privacy, software, hardware, algorithms, systems, and so on will all be covered. Samuel, maybe you want to say something about how participants can ask questions. And then once Samuel does it, Eduard, you'll be good to go.
Okay, so in case you have some questions, there are two options how you can ask. The first one, you can do that directly through the chat. You can find the option for a chat in the bottom menu and just put visibility to everyone. In that case, I'll try to read aloud your question, or I will try to unmute you so you can ask question yourself. And the other option is right next to the chat button, there is a participants menu. If you just open it, then what you can see in the bottom menu of this participant window, you can see a feature that's raised hand. And when I see that somebody raised his hand, I'll try to unmute you and you can ask a question that way. So these are the two ways how you can ask. And Eduard agreed that he's gonna regularly stop for the questions. So that's the window where you can ask. And also don't hesitate to ask us during a talk.
Great. Okay, Eduard, the floor is yours. Go ahead.
Okay, thank you. Again, hi everyone. And I would like to thank the organizers for the invitation and for organizing this great seminar. And it's a big pleasure to give a talk here. So today I'm going to talk about linearly converging error-compensated SGD, and this is a joint work with Dmitry Kovalyov and Peter Tarik from KAUST and Dmitry Makarenko from MIPT. So this is the outline of my talk. So I will start with the definition of the problem, and then I will describe common approach how to solve this problem, and then I will explain what is error-compensated SGD, or remind to those who knows about that algorithm, and then I will describe new methods developed in our paper, and present a unified convergence analysis that helped us to derive new convergence bounds for them. And in the end, I will say some words about experiments and other applications of the framework that I want to introduce today. Okay. In our paper, we are focused on distributed optimization problem. Here, we want to minimize some function f, and it depends on x, which can be parameters of the model. For example, d is number of parameters, and function f has a form of a finite sum. Okay, and we also have some network. And so we have some devices connected with a server in a centralized manner, and each device has, so we have n devices, and each device has an own function fi. So it can be a local loss function for the corresponding device. And these loss functions can be either in expectations or a finite sums, or finite sums. So it's a pretty general problem, and yeah. So we will assume that each individual function is L-smooth and convex, and which means these inequalities. And we also will assume that the average of these local functions is a strongly quasi-convex function. Actually, this means the following inequality. So it's just a relaxation of the regular strong convexity. Here, X star denotes the solution of the initial problem. So probably, are there any questions? Okay. So do not hesitate to interrupt me. Yeah. So, and probably one of the most popular approach to solve this problem is parallel SGD. In parallel SGD, at each iteration, server broadcasts the parameters xk to the devices. Then these devices compute stochastic gradients in parallel. So namely, they compute vectors gik, and these vectors are, for parallel SGD, we assume that these vectors are unbiased estimators of the true gradients of local loss functions. So yeah, and actually this expectation should be conditioned. It should be conditional expectation with frozen xk. Yeah. And then after they compute stochastic gradients, server gathers these stochastic gradients and perform an update, an SGD update where the descent direction is defined as an average of these stochastic gradients, and gamma is a step size. And then algorithm repeats steps 1 to 4. So good news are that this algorithm is very simple and it can be much faster than non-parallel version of SGD. But there is a big issue here. One of the issues is that communication can be very expensive, and in many applications, communication is a bottleneck. And in our paper, we are focusing on this, on reducing the communication cost, which is very relevant to federated learning applications. Okay, so how to handle the communication bottleneck? There are many approaches how to do that. For example, if we can change the topology of the network, then we can consider. Okay, there is a question in the chat. Okay. It was a private message. Yeah, I cannot read it, unfortunately. Okay, the first approach is to change the topology of the network, if you can do that, and it leads to decentralized methods. Another possible way how to reduce an overall communication cost is to do more work on each worker and communicate less. And for example, one can consider local SGD or federated averaging algorithm. So it can work better for some setups. But we will focus on the different approach that is based on the following statement trick. We can send less information at each iteration in order to reduce the overall communication cost. So, for example, we can, instead of sending stochastic gradients, GIK, for example, this vector, instead of sending this vector, we can send a compressed version of it. Let's say just we can take just we can keep only the component with the biggest absolute value. And we will call this operator as compression operator. And this is a natural question how to choose this operator. And so let us define the possibilities. So we will focus on two different classes of compressors. The first class is unbiased compressors or quantizations, and the second class is biased compressors. And from unbiased compressors, we will assume that the variance of unbiased compressor is bounded by squared norm of the input vector times some constant omega. This constant omega depends on the type of compressor. So, and from biased compressors, we will assume this inequality. So that in expectation, the squared difference between the input vector and the compressed vector is smaller than 1 minus delta times the squared norm of the input vector. And this delta is also depends on the compressor. Okay, for example, as an unbiased compressor, one can take a rand K operator. For example, let's K be 2, and for 5-dimensional vector, consider how does it work. So rand K just picks K components uniformly at random, and for example, it can give the following output, and then this operator multiplies this vector, the obtained vector, by some constant that depends on number K, number of picked components, and on the dimension. So here the dimension is 5, therefore we have 5 here, and we pick 2 random components, therefore we have 2 here. It is needed for unbiasedness. Okay, and for top, as an example of biased compressor, we can consider top K compression operator, and it just picks K component with largest absolute values. So in this example, top 2 compressor will produce the following output. Okay. Are there any questions? Okay, so let us move on.
I don't see any questions. If I see something, I'll let you know. But feel free to keep asking.
Yeah, I will keep pausing at some points. Good. In some places of my talk. Okay. So what can we do with these compressors? For example, with unbiased compressors, we can run the same parallel SGD, but instead of sending the gradients, stochastic gradients, we will send quantized version of that. And this is essentially QSGD and similar approach like Turngrad and DQGD. These methods, they have some sublinear convergence rates, even in the case when workers quantize full gradients. So, and there is a remedy in the paper about DIANA, how to handle this issue and how to obtain linearly converging method with quantization. So when workers compute full gradients. And so for unbiased compressors, we can obtain linearly converging method, both with stochastic gradients and when we quantize stochastic gradients in some special case, and for the case when we quantize full gradients. However, the situation changed dramatically when we consider parallel SGD with biased compressor. And in this paper by Alexander Beznosikov, Samuel Horvath, Peter Ritarik, and Mer Safarian, in this paper, authors proposed a simple example when parallel SGD with top 1 compression operator diverge exponentially fast. So they considered a quadratic problem with n equals e equals 3. I remind that n is number of functions and d is number of parameters. It's dimension of the problem. So, and in this case, parallel SGD with top one compression operator satisfies this recursion, and as a consequence, it diverges exponentially fast. So one can read the details in this paper, and probably one could ask a question: how to fix this issue? And the answer is one can use error compensation. And this leads us to so-called error-compensated SGD method. And this method was studied both from practical side of view and theoretical side of view in many papers. There are some of them. And so essentially, error-compensated SGD does the following steps. During the first step, server broadcasts the parameters, x0, it's the starting point. Then devices compute stochastic gradients in parallel. So they are obtaining these vectors g1, 0, g2, 0, and so on. Then devices do the compression. So they want to send this information, but because of the communication, but because they want to reduce the communication cost, they apply compression operators to this information, to this vector gi0, and send them to the server. And at the same time, workers save and send information locally. So the unsent information during the step one is gamma times stochastic gradient minus what we send. So that is why we have the following formula. And then server gathers the information, computes the average, and then using this formula obtain the next iterate. Okay, and then server has this next iterate x1, and devices keep these vectors that are called error vectors or memory vectors. They keep these vectors for the next iterations in order to try during the next iteration, in order to try them to send them later, or let's say partially send them. So during the step, during the second step, server again broadcasts new parameters. Devices again compute stochastic gradients in parallel, and now they use slightly different formula for the compression. So now they want to send both this vector E11 or EI1 and stochastic gradients. So they compute the sum of these vectors, then compress this sum and send the compressed version of this sum to the server. So now here the second guy in the sum is new information that devices wanted to send, and the first term it's just old information devices want to send, or just their memory. Okay, and then as before, they send these vectors vi1 and update unsent information. Now the formula for the unsent information is as follows. We need to take we need to take the initial vector and subtract the compressed version of it that we sent. Okay, and then server gathers the information and updates the parameters using the same formula. And devices update their memory. In general, step k+1 has the same form as the second step. So server broadcasts new parameters, workers compute stochastic gradients in parallel, then they do a compression using this formula and update their memory and send compressed vectors, and server updates the parameters. And then these steps repeated. Okay, and this method converges even with bias compressions operators. So, and the rated convergence is on the slide. So here, epsilon is accuracy of the solution in terms of functional value. So error-compensated SGD finds this point, hat x, satisfying this inequality after this number of iterations. And here, tilde hides logarithmical factors depending on epsilon, and delta is from the definition of the compression of compression operator, sigma squared. For simplicity, we consider here the case when stochastic gradients are unbiased estimators of the true gradients with uniformly bounded variance. So here sigma is a uniform bound for the variance, for conditional variance of the gradient. And we also have this term, zeta star squared, and it's just an average of squared norms of the local function at the solution. So somehow it measures dissimilarity of local functions at the solution. And in general, it is not zero when these functions do not share an optimizer. Okay, and one can notice that this method, error-compensated SGD, fails to converge with linear rate even when workers compute full gradient. And the reason is that we have here in the complexity bound we have zeta star squared. So in general, it is not zero even when sigma is zero. So even when workers compute full gradient. And one may ask a question, for example, but probably one may ask a question that is these bounds, are these bounds tight or not? Probably just our analysis has some artifacts, and that is why we do not succeed to show linear convergence rate. And the answer is that it is not an artifact of the analysis, of the existing analysis. And for example, we run error-compensated gradient descent, namely when stochastic gradients are just gradients, on logistic regression with L2 regularization. And this is a smooth, strongly convex problem, and gradient descent, as expected, it converges linearly. However, error-compensated gradient descent with top 1 compression or top 2 compression, it converges linearly only to some neighborhood of the solution, and the size of this neighborhood is proportional to zeta squared, zeta star squared. So we see that error-compensated method, error-compensated GD, fails to converge linearly. Okay, are there any questions? Okay, probably there are no questions. Yeah, and as I said, this behavior indicates sublinear convergence rate, and this indicates linear convergence rate.
So there is a question by
Ali.
So I'm going to read it. So does this depend on the way matrix A is defined?
So the convergence rate depends on the properties of matrix A. So the slope of this line depends on the maximal eigenvalue on the relationship between maximal eigenvalue of A transpose A and minimal eigenvalue of that matrix.
I see. So basically, you can define some A that it achieves the linear convergence like this, or it gets worse, or it just always works like this.
So, okay. For example, we can build such metrics that. Okay, let me show you. We can build such metrics that individual loss functions fi share the optimizers, for example, and then these lines will be so we will have linear convergence rate here. But in general, these functions are different, and therefore we do not have linear convergence.
Thank you.
Yeah, and the speed of convergence depends on the properties of this matrix A as well. And so there are two questions. Is it possible to design linearly convergent stochastic gradient descent with error compensation when workers compute full gradients, namely linearly convergent error compensated gradient descent? And is it possible to design linearly convergent SGD with error compensation when the local loss functions have a finite sum form? And in our paper, we gave a positive answer for both questions. Let me start with the new method, error-compensated GD star. So let me simplify the bound for error-compensated SGD and just consider the bound for error-compensated GD, gradient descent. So here, sigma squared is 0 because we compute full grade, workers compute or devices compute full gradients. And still we have here a sublinear term, and this term depends on the gradients at the solution. So one might ask a question, what if devices know these vectors from the beginning? So I mean, what if devices know this vector gradients as a solution from the beginning of the work of the method? And actually, one can use this information and shift the stochastic and shift the gradients by these vectors at the gradients at the solution and obtain linear convergent method. So this is the idea of error-compensated GD star. Server, as before, broadcasts new parameters to the worker, but now workers compute shifted gradients in parallel. Instead of computing just gradients at the current point, they subtract the gradients at the optimality and use it as GIK. And then the scheme of the method is the same as for error-compensated GD. The workers do a compression using the same formula, but with different GIK. They compute, update their memory, and server does the same update as before. But and what we can get? We can get the linear convergence rate. So to reach epsilon solution, this method error-compensated GD star needs the following number of iterations. So it's condition number over delta. Delta depends on the compression operator that devices use. And of course, we have linear convergence rate, but the method is totally impractical because it uses the gradients at the solution, and it is hard to compute them without knowing the solution. But our goal is to find the solution. Therefore, this method is impractical. And are there any questions about error-compensated GD star or about the complexity?
So I have one question.
Okay.
A planted question. So so why does this method work? Why does this subtracting these gradients at the optimum, intuitively speaking, why does that solve the issue? Shed some light on that.
Okay. There are two explanations. The first one is that this term goes from the proofs, and this goes from the analysis, and at some point we use a Young inequality, and because we do not have we do not have these vectors at some quantity in the proof, and when we subtract it from the stochastic gradients, then we have them, and this term do not appear here. But it's just algebraic. It's not intuitive explanation, and intuitively one can say that. Okay, imagine that. Okay, imagine the situation when the memory is 0. Okay, imagine the situation when the starting point is the solution of the method. So the method should not the good method should not go from this point somewhere. So the good method needs to stay at the solution, and but when we use this GI case, just gradients at xk, which is x star, for example, without these shifts, then workers compress this information and send this information to the server, and the server average this vector, and this vector is not 0 anymore, because if the average of GIK will be 0, but when xk is x star, but not the average of compressed terms. And this is one intuition that.
Okay, thank you.
This method does not have fixed point property, initial method, and this is how we obtained this property. Or yeah. Okay, we have such methods with good linear rate, with a good rate, but it's impractical at all. And the question is, how can we develop a practical analog of this method? And this is how we develop error-compensated SGD-DIANA. So basically, this method follows the same scheme as error-compensated SGD, but now the key feature, and the key distinction from plain error-compensated SGD is in the way how we define GIKs. So here the first part is an unbiased estimator of the true gradient of the local function, and then for example, you can imagine that GIK hat is just gradient of fi at the point xk. And since we do not have the gradients of local loss functions at the solution, we are trying to learn them during the optimization, and that is why we introduce here this shifts HIK plus HK. And the way how we learn intuitively, this sequence is needed to approximate the gradients of local loss functions at the solution. And this is the way how we learn these gradients at the solution during the iterations. And here, workers, here Q of this gradient differences, this Q it's an unbiased compression operator that was defined at the beginning of the talk. So it's an unbiased compression. We use both a biased compression operator and an unbiased compression operator. So, and workers also send, they send VIKs to the server, and they also send these quantized differences to the server, and the server average these vectors IK. Actually, one can write the same formula for the update of HK. So we will have HK plus 1 equals HK plus alpha times times average of quantized differences. So server can compute this vector hk and can send them back to the workers. And as I said before, the key intuition behind this sequence is that it helps us to approximate the gradients as a solution. And we have here an extra term hk because we want to keep the average of gik. We want to keep this average unbiased, to be unbiased estimate of the average function, so of f. So there is a question in the chat. Why don't we use directly the correct gradients to update h instead of the compressed version? So yeah, here, for example, by the way, do you mean, Otman, do you mean that?
Yeah, exactly. So I mean, this question, why don't you use directly? Why are you compressing before adding, updating them to the memory instead of using directly the correct version? Normally, it will reduce the variance more than if you use the compressed ones.
Okay, right? Yeah, because we want to send this information to the server and to keep this vector gik unbiased. Each worker needs to know this vector hk. That depends on the information from other workers. So it means that we need somehow to communicate this information through the server to other workers, and that is why we use quantization or unbiased compression here.
Okay, so then I have another question in that case. So now you are sending both H and G to the server, right?
Now we are sending via IKs these vectors. It is a compression of memory plus stochastic gradients, GIK times gamma, and we are sending only this part, not all HIKs, but only the updates for them. Yeah. And so we initialize them by zeros, vectors of zeros.
So this doesn't answer what I asked in the beginning. If you are doing this, then okay, you can send V, but to update H, you use the complete one without compressing. So to update H, you use the complete information from gradients, and then you just compress the error compensated term after computing Z. I mean, so you don't need to. Yeah. You don't need, because this term is not sent, and you are just reducing the amount of information you are using to update it. This is why I don't get really. So I don't see why we are using this term here. It's not necessary for communication, in fact.
You're right, but for the analysis, we need to have. I will show you later that we need to have an expectation that average of GIKs is an unbiased estimator of function f at the point xk, and we take the expectation conditioned on xk, and that is why we cannot use here the definition for HIK without compression and for HK with compression. Then it will break unbiasedness.
Mm-hmm. Okay, yes, thank you.
It's just for the analysis, but we didn't try to use the schemes that you mentioned in the experiments with without the compression here and with compressions there.
Mm-hmm. Okay, I see. Thank you very much. Thank you, Eduard. Thank you.
Thank you for the question. Okay, and what is the rate of convergence of error-compensated SGD-DIANA? So the rate of convergence is following. Actually, there are two options for the rate. The first option is to, and it depends on how we choose this parameter alpha. So if we choose alpha to be 1/1 plus omega, then we get this rate. And if we choose alpha smaller, if we choose alpha to be delta over 1 plus omega, then we will get this rate. So these bounds are not directly comparable, because in this bound, the last term is worse than the last term here, but the first term is better than this one. And so in some regimes, for example, when sigma is big, then and when these terms dominate this one, then this bound is preferable. And when sigma is small, then this option is preferable. And as before, tilde here hides logarithmical factors depending on epsilon, on the target accuracy. And if sigma is 0, if workers compute full gradients, then we get the desired property. We get error-compensated SGD-DIANA, the methods that converge linearly even without knowing gradients as a solution. And the rate of convergence is as following. Here we have omega. Omega here reflects the rate, how fast our HIK, our workers learn the gradients as a solution. So if we will take here alpha to be 1 over omega plus 1, then the rate of learning will be, roughly speaking, omega, capital O of omega. So this is the rate of error-compensated SGD-DIANA. And but actually we can do more if we assume that the local loss functions have a form of finite sums. Okay, and this leads us to a new method called error-compensated loopless SVRG-DIANA. Actually, it's very similar to the previous method, error-compensated SGD-DIANA, but now we change the definition of GIK head. Now, instead of choosing just a stochastic gradient, we apply a variance reduction trick. We use loopless SVRG estimator instead of GIK head. And here, L, this number L, is picked uniformly at random from 1 to m. And WIK, this point is called reference point, and it is updated with some small probability. Actually, with probability p proportional to 1 over m, we update this reference point to be the current iterate xk. So it means that with small probability, we need to compute the full gradient of the local loss function, and with large probability, we compute only stochastic gradients, only the gradients of the terms of summons. And these shifts are needed to reduce the variance coming from the stochasticity of the gradients, like in the classical variance reduced methods. And here we combine variance reduction in the classical sense with variance reduction coming from compressions, which DIANA does, and with error compensation. And the rate of convergence of error compensated loopless SVRG-DIANA is omega plus m, number of functions on the worker, plus condition number over delta. So we have good interpolation. So when omega and delta are when we do not have any compressions, then our rate recover the rate of loopless SVRG. And when the number of functions, local functions m equals 1, then we recover the rate of error compensated GD-DIANA. So these bounds are tight, and they in the special cases they correspond to the known tight rates. Okay. Are there any questions about this new method, error-compensated loopless SVRG-DIANA?
I would have one question, Eduard. Yeah,
Okay.
so if you look at your rate, and like you see that this delta parameter, that it doesn't decrease with increasing number of nodes, and this is, for instance, this is something that happens when you use unbiased compression, right? You can go like you can almost have no effect of compression once your number of nodes grows. So
Yeah.
do you think that like the analysis can of error feedback can be improved, that you would see such effect? Or do you think that because of the way that you keep error locally for each node, do you think that this is the best you can hope for?
I guess this is the best we can hope for, because for error compensated GD star, we have the following rate. And so it's the most simple situation.
But is it the lower bound?
So actually, I'm not actually, one can accelerate this rate, and there is a recent paper by Peter and co-authors, and actually they have an accelerated version of error-compensated SGD. So
yeah,
it's not a lower bound, but
yeah.
I do not know how
yeah,
tight.
Yeah, whether you
At
think
least,
that n can be there or not.
I'm not sure.
That's like I'm not asking like with respect to like the standard acceleration. I'm just asking like, can you obtain such rate that n would be there? That like the kind of the standard thing that you would obtain for unbiased compression, or is it the price you have to pay once you move to the biased setting?
My intuition say, I do not know the rigorous answer, but my intuition says that we cannot obtain the division by n in delta there for biased compressors.
So
but,
I have something to say about this, if I may. So I don't believe without additional assumptions one can do that. But if you assume about the compressor C some things, and there's few things that one can assume, additional things then this will happen. And one of them is that on expectation, you get a multiple of the input. If you assume this is kind of an unbiasedness, scaled version of it, then one should get this divided by n. And there's also another more complicated assumption, some sort of an average contraction assumption, which can lead to something like this, but this was not explored for this method, for this particular method before.
All right. Thank you, Peter, for the comment, and thanks Samuel for the question. Okay.
There's a question, another one by Othman, so I'm going to unmute you. Or maybe Samuel can be faster and do that, because I'm scrolling and I can't. Okay.
I was just wondering, so the results that you were presenting had like this term W on them. So this means that you are using the unbiased version of compression, I mean. And my question was if those rates are also valuable for biased compressors or not. The rates for DIANA and EC-LSVRG-DIANA.
So in DIANA paper and variance reduced DIANA paper, it is crucial to use unbiased compressors. Or do you mean that here and here it is also crucial to use unbiased compressors?
Okay, thanks.
Yeah, thank you. Okay, and now I have introduced the new methods, and probably it is good time to say how can we analyze them and how did we obtain these rates. And our analysis is based on another paper with Philip Hanzelli and Peter Ritarik. about unified theory of SGD. So in that paper, for simplicity, I just show there's a problem without composite term or without regularization. So in that paper, we consider minimization of f of x, and where f can be either an expectation or finite sum. And we consider, we developed a unifying view on SGD type methods. So we consider the method of this form, xk plus 1 equals xk minus gamma gk. And here gk, and we introduced a new assumption on gk. This assumption is just unbiasedness of gk, conditional unbiasedness of gk, and also two extra inequalities. So the first one, it reflects just smoothness properties of the problem. Actually, this one, and noises introduced by stochastic gradients. It's just some inequality for the expected squared for the second moment of the stochastic gradient, and our assumption has another inequality, and this inequality is needed for variance reduced method, and it describes the process of variance reduction. And under this assumption, one can analyze a lot of methods, and here are some of them. So one can analyze simple SGD, stochastic SGD with arbitrary sampling, variance reduced methods, methods with coordinate-wise randomization, and even DIANA. So methods with quantization, and also one can put in this framework QSGD as well. And so there are a lot of methods covered by this assumption. And under this assumption, we prove the following theorem. So if the step size is not too big, then iterates of SGD satisfy the following inequality here. So it's just an upper bound for the expected square distance to the solution. And actually, at each for all known special cases, our result recovers the sharpest rates. And in that paper, and also we developed some new methods. And if you want to know about details, please look at the paper and find these details. But today I do not want to focus on that type of assumption, and I just want to introduce a new assumption that helped us to analyze methods with error compensation in a unified manner. So the modified assumption is as following. Here we also have kind of unbiasedness, but now we assume unbiasedness of GK, where GK is an average of GIKs, average of local stochastic gradients. And now I need to explain these inequalities. So, but I will explain them only at the high level. So the first three inequalities, they also reflect some smoothness properties of the problem. So especially these terms, and the noises introduced by both compressions and stochastic gradients. So then this inequality describes the process of variance reduction of the variance coming from compressions. And the last inequality describes the process of variance reduction coming from the variance from stochastic gradients. Okay, so here we have the difference between this assumption and the previous one is that instead one inequality needed to reflect smoothness property and noises, we use three inequalities because these constants, they affect the rate differently. And also we introduced two sequences of sigma case instead of one in order to handle these processes of variance reductions differently. And here is the informal statement of the main theorem. So the main theorem says that under some assumptions on gamma, the step size, we have the following rate of convergence. And here we have an exponentially decaying term, and the rate of convergence exponential decay here is as following. Row 1 and row 2, they are coming from the key assumption, and gamma mu is a regular term. This quantity depends only on the starting point and the step size, and the last term depends linearly on the noises, D1, D1 tilde, D1 prime, and D2. These noises are coming from the key assumption. Okay, and actually using this theorem, we in all special cases we recover the sharpest rates and develop new methods and prove new convergence bounds for them. And here are some of new methods developed in our paper. And in this talk we just mentioned error-compensated SGD, error-compensated GD star, error-compensated SGD-DIANA, and error-compensated loopless SVRG-DIANA. But actually, one can combine different local stochastic estimators. For example, one can use Saga estimator for GIK, and one can do coordinate-wise randomization there. And actually, we just put in the paper only a few examples of these combinations with DIANA trick and with variance reduction of the variance coming from the stochasticity of the gradient. So there are a lot of possibilities. And actually, in our paper, we use slightly simpler framework, which is more general and which helps to analyze methods without error compensation, for example, and methods with delayed updates as well. Okay, and here are some experiments. So it's again logistic regression with L2 regularization, and as we can see, for example, error-compensated loopless SVRG without DIANA trick does only a partial variance reduction. So error-compensated SGD and error-compensated SGD-DIANA with different quantization operators, they stop to converge earlier because the noise coming from the stochasticity of the gradients dominates in this particular example. It dominates the noise coming from compressions, and therefore, since these three methods do not use variance reduction in a classical sense, they stop earlier and start to oscillate earlier. And error-compensated loopless SVRG, it does partial variance reduction. And when we apply DIANA trick, combine it with DIANA trick, we obtain the full variance reduction. And as a consequence, linear convergence rate. Okay, and as I said before, our framework is very general and helps to obtain, as a special cases, a lot of methods. Here are some of them. For example, methods without error feedback, like SGD with arbitrary sampling, Saga, LSVRG, QSGD, Turngrad, DIANA with two-directional compression or bidirectional compression under arbitrary sampling assumption, variance reduced DIANA, JAG sketch, Saga, and also our framework covers methods with delayed updates, and here are some of them. So, and actually, I didn't say anything about analysis for non-strongly convex objectives, but our main theorem works for regularly convex case as well. So in one theorem, we established results for strongly convex or strongly quasi-convex case and convex case. And as I said before, in one theorem, we recover the sharpest rates for all known special cases. And okay, that's all I wanted to say. Thank you for your attention. And are there any questions?
Thank you, Eduard, for the very nice talk. If there's any questions, feel free to ask. We'll be happy to unmute you and you can ask directly. So Igor is asking a question. Can we unmute him somehow? Let me scroll.
Okay, thank you for the talk. The question is, if you consider error-compensated SGD, does it become simply a distributed SGD in case of identical compression? I mean, when we have no compression,
Yes, because we initialize EI case is zeros, then, okay, let me go back to the slide with error-compensated SGD. Okay, as I said before, we initialize our memory vectors EI case with zeros. So here we do not use them in the compression. And when the compression is identical, then this vector equals gamma times G1 0, for example, here. And then our error vectors will maintain them zeros. Okay. And then on the second step, we will do the same. And if this is 0, then the new memory vector, the new error vector will be also 0. And that is how. And if this is 0 and compression operator is identical, then we will have 0 memory vector forever.
Any more questions, anyone? Yegor Shulgin is asking a question. Let's unmute him. Yegor, you're unmuted.
Hi. Thank you for the talk, Eduard. I just wanted to ask you to clarify what do you mean by this delayed updates.
Yeah,
I guess
so
on the last slide you mentioned it.
Yeah. I mean that in Z methods, we assume that stochastic gradients are computed at some previous point. So with some delay, let's say tau, we compute the gradient. So not at the current point, but at some point not at iteration k, but at iteration k minus tau.
Mm-hmm.
And
tau is fixed for the whole process.
Yeah. Tau is fixed.
Mm-hmm. Okay, thank you.
Thank you for the question.
So I have another question, and that is, so you described a framework which covers many methods. So what does this framework not cover?
Okay, so this framework do not cover, I forgot to add this, but it do not cover a lot of things. For example, it does not work for composite problems, so it does not cover proximal versions of these methods, for example, and it does not cover proximal version of error-compensated SGD, and yeah, and also it do not cover accelerated methods. For example, it do not cover methods like Katyusha and accelerated SVRG and so on, and it do not cover the fresh method from your paper about error-compensated accelerated SGD. So yeah, and also it do not work for. It works only for the simple coordinate-wise randomization, and so and also.
Do you see any other application of it beyond error compensation and delayed updates?
So it makes some insights. So it can be used for, I think, similar methods. So for example, it just this approach just think that we can modify this assumption somehow and for the suitable class of methods, and then get a unified convergence analysis. But yeah.
But not in the current form. You would need that would need to be
Probably not in the current form.
Okay.